Hello and welcome to the AI Research Roundup. I am Alex. Today is May 10th, 2025. Alright, so today we are looking at a paper from Hugging Face's trending list, published just 8 days ago on May 2nd, titled Rethinking RGB-Event Semantic Segmentation with a Novel Bidirectional Motion-enhanced Event Representation. This research paper tackles combining regular camera images with data from event cameras, which capture motion, for semantic segmentation. This means teaching AI to label every part of a scene. It proposes a new way to represent event data, the Motion-enhanced Event Tensor, or MET, making it dense and better aligned. Okay, so this first visual really illustrates the core problem and their solution. On the left, we see the traditional grid-based approach. You have the event stream, those sparse motion signals, and the regular RGB video stream. Combining them directly can lead to spatio-temporal misalignment, where timing and location do not quite match between sensors, and modal misalignment due to different data types, yielding sparse features. On the right, their proposed Motion-enhanced Event Tensor uses optical flow, an estimation of object movement, to create dense, continuous, and temporally aligned event features, better matching the RGB stream. So building on that idea of the Motion-enhanced Event Tensor, this next figure illustrates the Motion Enhancement Estimator, which is the component that actually creates it. We see it takes the optical flow and the event temporal features as inputs. These are processed through several steps, including a type of neural network called a multi-layer perceptron, a fast Fourier transform, or FFT, which helps analyze signals by breaking them into frequencies, and a deformable convolution layer, which is a smart filter that can change its shape to better focus on important details, ultimately producing that denser motion-enhanced event tensor. Alright, this diagram gives us the big picture of their entire system, called BRENet, which stands for Bidirectional RGB-Event Semantic Segmentation Network. It takes the regular camera image and the event stream. The event stream is processed to create those motion-enhanced event tensors we discussed, now in forward and backward directions. These, with image features, go to the Bidirectional Flow Aggregation Module, or BFAM, which merges image and event data using signal frequencies. Next, the Temporal Fusion Module, or TFM, further refines this, ensuring good spatial alignment using deformable convolutions before producing the final segmented output. Following the overall BRENet structure, this figure details its Bidirectional Flow Aggregation Module, or BFAM. It processes the forward and backward motion-enhanced event tensors and the image features. Notice the use of fast Fourier transforms to analyze these inputs based on their frequencies. Then, Part A shows spatial attention, which is a mechanism that helps the system focus on the most relevant areas in the scene. Part B shows channel attention, which then helps select the most informative types of features. Finally, inverse fast Fourier transforms convert the data back, producing refined aggregated features. Okay, so this table presents baseline comparisons on two datasets, DDD17 and DSEC. It shows how their BRENet method, using the Motion-enhanced Event Tensor, stacks up against other existing approaches. We see metrics like MIOU, which stands for mean intersection over union, a measure of how well the predicted labeled regions match the actual ones, and overall accuracy. Crucially, BRENet achieves the highest scores on both datasets. For instance, 78.56 mean intersection over union on DDD17, significantly outperforming the previous best. This really underscores the effectiveness of their proposed components in improving semantic segmentation. Building on those impressive overall results, this next table shows an ablation study on the DDD17 dataset. An ablation study is like taking a car apart piece by piece to see how important each part is for making the car run well. Here, they are doing that with their BRENet system. We see that their Motion-enhanced Event Tensor alone in row 6 already outperforms other event representations, achieving a 74.32 mean intersection over union. Then, including components like bidirectional propagation, which means processing event data both forwards and backwards in time, the Bidirectional Flow Aggregation Module and the Temporal Fusion Module leads to further improvements. The table shows that the full system, with all these parts working together, achieves that top score of 78.56. So, as that ablation study showed, every component of their system, BRENet, which is their bidirectional RGB-Event Semantic Segmentation network, is vital. The core idea is how their new Motion-enhanced Event Tensor, making event data dense, plus modules like the Bidirectional Flow Aggregation module for merging sensor inputs, and the Temporal Fusion module for precise alignment, work together. These parts effectively fix misalignments between camera and event data, leading to top-notch semantic segmentation. This work really pushes forward how we fuse these visual streams. That is all for this AI Research Roundup. Thanks for tuning in.